In this third example of the conservation of mass for finite control volume, we're going to up the complexity a little more. Two ways. One, it's going to be an unsteady problem. And two, we're going to allow velocity profiles to vary over our areas so that we actually have to do some integrals. So again, this is the conservation of mass. It's the derivative of mass with respect to time, the rate of change of mass, this integral of rho dv. That's just rho times the volume. That's the mass, time derivative of that. And the second term here looks like rho va, and it is, except that we have to integrate it because v can vary over the face that we're interested in. And we only care about the component that is normal to the face, and so we define these normal vectors and then use a dot product to get there. So here's the problem statement itself. We have a very strangely shaped container with three inlets or outlets. Station 1 here has a uniform flow going in. Station 2 has a uniform flow going in. Station 3 here is on an angle. In other words, it's not perfectly lined up, say, with the XY coordinate system. And it's got a non-uniform profile coming out that is given by this equation as a function of radius, and so this must be a round flow area. In other words, the cross-sectional area must be some sort of a circle. Because it's told to us that it is unsteady, what that means is that this thing could be filling up or draining as a function of time, and we're asked to find what's the mass in our system as a function of time, and we're told to assume that the velocity profiles going in and out are not functions of time. In other words, there's steady flow rates going in and out. What's happening to the mass of our system? Well, just looking ahead a little bit, well, we've got the geometry in front of us. We know that we're going to need a bunch of v dot n's, 3 of them to be precise. So let's define our normal vectors. First off, we want n hat 1. Remember, they always point out, so n hat 1 points that way. N hat 2 also points out. And n3 is on an angle here, like so. N hat 3. And again, this could be a combination of x and y at some angle theta with i's and j's. Or, like in the last example, we could recognize that we can get away with a little trick here and just call it direction 3, e hat 3. Excuse my sloppiness there. Let's fix that. E3. Because once we do the dot product, since all of the velocity is in that direction anyway, it's going to save us from actually having to do the trig. Okay, so let's work the vectors out real quick that are going to show up inside of the second integral term here. We know we've got one for a1, 2, and 3, so it's going to be 3 of them. So v1 dot, v1 is equal to u1 magnitude, u1 times the unit vector in the x direction, which is I hat. We can look there at n1, and like in several examples before, it's pointing in the negative x direction, so that's a minus I hat. And that lets us write that v1 dotted with n1, v1 dot n1 is equal to u1 I hat dotted with minus I hat, which is just minus u1. v2 here at the second inlet, same story. It's horizontal, so it's in the I direction. So we have u2 I. n2 points in the negative x direction again. It's still a minus I hat. And so v2 dot n2 is equal to u2I dotted with minus I dotted with minus I, and that's equal to minus u2. The one that's a little strange is this third one, so let me show you my notation here. v3 is going to be a magnitude of, let's just call it u3, except it's a function of r, so I like to write function of r in parentheses here, and it's in the e3 direction. And all this tells me is that it's not a single number, it's some function. Which function? Well, this one they gave us. n3 happens to be in the E3 direction. We picked that, so it would be convenient, E3. And so we can write then that V3 dot n3 to go into the third integral that's going to show up is u3 of r times e3 direction dotted with e3, which is just equal to u3 as a function of r. So we're going to refer back to these dot products here in just a minute. Okay, so now we'll actually solve the problem here. We're going to conserve mass. How are we going to do that? Well, d by dt, integral over the volume of rho dv, plus integral over the areas of rho v dot n dA, and all that better equal 0. Well, as I said when we were introducing it, that's just the mass of the system. And so for incompressible, where rho is a constant, which it is, we can just jump right ahead and say this is d by dt of m of t plus the integral over the areas of rho v dot n dA, and that better equal 0. Well, that's great, because that's the thing we're ultimately going to be looking for is m. And so I think we can get one more line on this page. Now let's just go to the next. So add a new page here. We're going to sub into that. We'll just expand it by 1. Let me get us some room to write here. There we go. And so what we can write then is dm dt. This is just one line down. Now we're going to break the area integral up into the 3 areas. So integral over a1 of rho v dot n dA plus the integral over a2 rho v dot n dA, and the integral over a3 rho v dot n dA, and that's got to all equal 0. Now we already worked out what these vectors are. That's what we did the work in red there. So let's sub them in real quick. dm dt plus the integral over a2 of minus u1, I'm sorry, integral over a1, integral over a1, sub in for u1 there, rho dA, plus the integral over a2 minus u2 dA, oh, left out a row there, rho dA, plus the integral over a3 of u3, which is a function of r, times rho dA, and all that equals 0. Let's get as convenient as we can here. We can pop the first 2 out because they're constants, so we get dm dt minus u1 rho integral over a1 dA plus, oops, it's going to be negative, so minus u2 rho integral over a2 dA plus, we can pull the rho out of the third one, but not the u3, over a3 u3 of r dA equals 0. And now we have a problem. This business here, we actually have to do a little bit more work on. Okay, why? Because dA here, well, this is the circular face, and so that's the r d theta dr cross-sectional area there. And so this integral becomes the integral from 0 to r, integral from 0 to 2 pi, because it's a full circle. We're going to sub in the definition they gave us, which was u max times 1 minus r over big R squared times little r d theta dr. And I trust that you can do math. We're just integrating with respect to r and theta here. And the result of that is going to be pi big R squared over 2 times u max. Well, that's neat. So we can sub that in here and finish the work that we're doing. dm dt minus u1 rho, the integral here just becomes a1, minus u2 rho, this integral just becomes a2, and we already did this integral here, which becomes plus rho times pi r squared over 2 u max, and all that had to be equal to 0. But we're looking for mass as a function of time, so we've got one more set of integrals to do. We've got to get the dt over here, and then we can integrate. Why? Because nothing on the right-hand side is a function of time. u1 rho a1 plus u2 rho a2, just moving everything to the other side, minus rho pi r squared over 2 u max. We're going to take all of that, multiply it by our dt, and now we can integrate, right? Integrate this side, integrate this side. This side's going to go from our initial mass, which we could call m0, to m. This side we're going to integrate from 0 to t for whatever time it is. And that's going to give us a thing that looks like this. M of t. No t's show up here, so it's just all that stuff again. u1 rho a1, u2 rho a2. Clearly we could have cleaned this up a little bit, but we didn't, so who cares? R squared over 2 u max. And all of that is going to be multiplied by t. And we're going to add to it m0, this constant of integration business, right? Because this just became, this side became m minus m0. So I left m here, moved m0 to the other side. And so this gives us the mass as a function of time in that tank.